اوکی. اولا از دکتر پرهامی که دعوت ما رو پذیرفتن، تشریف آوردن، واقعا سپاسگزاریم. آقای دکتر پرهامی اکثر کسانی که اومدن کاملا میشناسن ایشون رو، خیلی نیاز به اینکه من توصیف بکنم شرح زندگیشون رو اینجا شاید نباشه، ولی در حال اونطور که رسمه اگر اجازه بدن من چند دقیقه صحبت میکنم. دکتر پرهامی در دانشگاه تهران، دانشگاه فنی، تحصیلات کارشناسی رو انجام دادن. بعد برای ادامه تحصیل به University of California لس آنجلس رفتن و پس از اون با مراجعت به کشور در داخل ایران کارهای مختلفی رو انجام دادن که عمده‌ترینش همین استادی دانشگاه صنعتی شریف و جزو کسانی که رشته ریاضی کامپیوتر رو در واقع راه اندازی کردن، قسمت کامپیوتر در دانشکده ریاضی و کامپیوتر رو راه اندازی کردن. انجمن انفرماتیک و فعالیت مختلفی که در اون دوره داشتن. تا چند سال پس از انقلاب هم در ایران تشریف داشتن، ولی بعد از اون اول به کانادا و سپس به ایالات متحده رفتن و الان سالهاست که در دانشگاه کالیفرنیا در سانتا باربارا مشغول به کار هستن و تألیفات بسیار زیادی دارن که شرحش رو در اون مختصری که هومن جان زحمت کشیده بودن گذاشته بودن ما نوشتیم و من اینجا دیگه مختصر میکنم و از دکتر پرهامی خواهش میکنم که صحبت خودشون رو در زمینه Recursive Methods for Synthesizing Digital Circuits شروع بفرمایند. قبل از اینکه حالا آقای اپهیرم یه لحظه، همه خودشون رو معرفی کردن عبدی جان، اگر شما میخواید یه لحظه خودتون معرفی کنید. در من خیلی خوشحالم که شما رو دیدم.
لطف دارید، خیلی ممنون. منم خیلی خوشحالم همه رو میبینم. دکتر پرهامی و بعد از 30 و نگیم بهتره این همه سال میبینمشون. اولین استاد راهنمای ما بودن و نمیدونم حالا معرفی باید بکنیم خودمونو بعد از 30-40 سال.
فقط این که کجا هستین و چه رشته؟
من اسوسییت چر، پروفسور و پروگرام دایرکتور دپارتمنت آف کامپیوتر ساینس رایرسون یونیورسیتی تورنتو هستم.
بسیار عالی. خب دکتر پرهامی، ما به گوش شما هستیم. در ضمن قبلا صحبت شده بود که هر زبان فارسی یا انگلیسی مایل باشید میتونید صحبت رو انجام بدید.
بله، البته مثل که تصمیم نهاییمون شد که انگلیسی شاید ساده تر باشه، ولی هنوزم اگر ترجیح بدید فارسی من مسئله ندارم.
نه انگلیسی بسیار عالی. فکر کنم توی متن هم نوشته بودیم که به زبان انگلیسی است.
بله. بسیار خوب، یک لحظه به من اجازه بدید. تا اسکرین شیر رو را بندازم و بعد اوکی فقط خب همه این اسلاید عنوان سخنرانی رو میبینن؟ بله بسیار خوب. من در طول سخنرانی با این کرسر به اصطلاح به چیزهای مختلف اشاره میکنم. متاسفانه امکان این که بنویسم و به اصطلاح یادداشت بذارم روی اسلاید الان ندارم، ولی فکر کنم این کافی باشه. خب اول خلاصه چیزایی که میخوام بگم. من سعی میکنم زیر 1 ساعت صحبتامو نگه دارم و بعد اگر سوالاتی بود با کمال میل در انتها جواب میدم. دم کمه و سوال جواب زیاد مشکل نخواهد بود. خب اول یه چند کلمه راجع به اینکه طراحی سخت افزار، نمیدونم چند نفر از حضار به اصطلاح سخت افزاری هستن و چند نفر نرم افزاری، ولی زیاد اطلاعات سخت افزاری لازم نداره این صحبت هایی که من میکنم. فقط مقدمات طراحی، من اتوماتیک فارسی صحبت کردم. همه میفهمن صحبت های من رو؟ مشکل ندارن؟ Okay, I'm going to switch to English. So an introduction to hardware design, then the concept of recursion, which is very elementary, most people know about it, but to make sure that we are on the same page, I'll say a few words. Then I'll give you an example where recursion is applied at the algorithm level, at the software level, and hardware level, to show you that this is a very general concept and can be applied across the board. Although in hardware, it is applied a little bit differently, and I'll talk about that as I go through the examples. Then I'll give you 3 examples. 2 of them, one of them, the first one is very well known, fast Fourier transform, an algorithm that is implemented recursively and it's very efficient. Then still a known example, but maybe not as well known among all the computer specialists, designing multipliers and squarers. There are some interesting examples there. And finally, designing what I call counting networks. So that's my recent research that I'm going to describe to you. I've applied these recursive methods to the design of counting networks. Then a few words about advantages and drawbacks of using this recursive design strategy. And finally, conclusion and future work. Okay, so hardware design is a very time-consuming and work-intensive activity. It used to be that hardware was much simpler than software. Software has been complex for decades now. But hardware has become very complex only in the last 1 or 2 decades. So the process is very expensive and error prone. It's not uncommon for a company working in hardware design to assign teams of dozens of engineers to a particular project. And they work maybe for months, sometimes years, for bigger projects to design a piece of hardware. So they're faced with the choice of algorithms for designing the hardware, the technology to be used for implementation, and then the design process or methodology used. Now, the common way of doing things nowadays is to design a quick proof of concept. So because hardware is so complex, waiting until all the pieces are in place before testing it and verifying it is not practical. So just as people have done for ages for software, we tend to design a quick proof of concept, something that works, but maybe does not have all the features, all the bells and whistles, so to speak, and then add features to it gradually, testing and making sure it works after the addition of each feature. So this basically makes testing more manageable because you have a system going rather quickly, and then each time you add one capability, you test it again. So you test basically a small part rather than testing the whole system at once. And then we fine-tune the design. Sometimes this fine-tuning adds complexity and therefore errors to the design. So the bulk of errors basically are introduced in that fine-tuning and adding features and optimizing for speed and so on. Now, in some cases, there are many applications. You know, we are all conditioned to think of iPhone. You know, we are designing something to be put in iPhone. And if you want to put something in iPhone, then it has to be highly optimized. And you can afford to spend a lot of time and money on it. because you're going to build millions of those devices. But the bulk of digital systems that we design are lower volume, and speed, power efficiency, and things like that may not be as important as reliability and correctness of the design. One classical example of this is NASA. When NASA puts a computer on a spacecraft, they often intentionally don't use the latest technology, the most advanced technology, because older technology are more proven, they have a track record. More people are familiar with them and design methods and so on. So they purposely put something that is a generation or two older than the most recent technology, because they care mostly about reliability. And other things, hardware properties such as modularity, packageability, reusability, testability, these are what we call in the area of dependable computing the IEEEs. These are all words that end in IEEE, so the nickname for them is IEEEs. All these IEEEs are sometimes more important than the main attributes of speed and power efficiency. So we sometimes opt for simpler designs and older technologies. One final point.
Sorry, Dr. Parhami, there were a couple of messages about the slides. If you intend to move on the slides, it is not showing for us. We still see the first slide.
Oh, it's still on the first slide?
Yes.
Oh, I'm on slide 3.
Somehow we don't see the slides moving.
Okay, let me see. Do you see the next slide now?
No.
Okay. Okay, let me see if I'm sharing the right screen. Just 1 minute, I'm gonna. Okay, something's amiss here. Yeah, I don't see the zoom controls on my screen. Let me try to locate those. Yeah, this is very weird. Oh, okay, the zoom controls are here. I'm gonna stop sharing now for a second and then go back to sharing. Okay, what do you see now on the screen?
Slide 4.
Slide 4.
Now
Okay.
it's fine. Yeah.
Okay, good. So I guess we got back to. So I'm going to keep it where it is. It's on a different screen, so I'm going to look sideways as I. Okay, now I don't know about your meetings when you have in-person meetings, but the meetings we have here for IEEE in Santa Barbara, we often share, serve pizzas. Do you see the picture of pizzas?
Yes.
Okay. So these are recursive pizzas in line for the topic of my talk, pizzas within pizzas. An attempt at humor. Okay, so here is my example. So I'm now on slide 6. This is an algorithm called selection sort. You see here a list consisting of elements x0 through xn minus 1. I'm trying to sort this list. So selection sort is the algorithm that says find the largest element in the list. So basically scan the list once all the way to the end, and you identify that the maximum largest element is this xj. swap that element with the last element of the list. Do you see my cursor moving?
Yeah, yes.
Okay, good.
Yes, we do.
So when you swap xj, which is the largest element, with xn minus 1, now xn minus 1, the largest element is now at the end of the list, and therefore it's in its sorted place. And then you sort the rest of the list, which consists of n minus 1 elements. So this is a very simple sorting algorithm. It's not very efficient, but it's easy to understand. It's very easy to code. Basically, the recursive code for that is only a few lines. It's almost impossible to commit an error in this algorithm. Therefore, it's easy to test and verify. By contrast, if you use quicksort, which is one of the faster sorting methods, the code will be much more complicated and more likely to contain errors. So that's one of the advantages of recursion. Okay, so this is the algorithm explained in this diagram. This is the software, the code. Of course, it's a pseudocode. It's not in any specific language. And now if I want to design a hardware sorter using this principle, here is what it would look like. So each of these small boxes is a comparator that compares two inputs and forwards the smaller of the two to the top output and the larger of the two on the bottom output. So the larger of these two, x0 and x1, goes on this line. And then it's compared with x2. The larger of those two goes here, and so on and so forth, until after all these comparisons, this is the largest element. You output that, and then you sort the remaining n minus 1 elements, okay? So this is a recursively designed sorter. So this is the distinction I want to make. When we talk about recursion in hardware, it's often the design process that is recursive, because the hardware is actually fully unrolled so that there's no recursion when it executes. Okay, so recursion is only at the design stage. So this is a simple design principle, leads to a circuit that I'm fairly confident will work correctly. Now, if I unroll this, now if I represent these comparator boxes with just vertical lines to make it easier to draw diagrams, this set of comparators here, they look like stairs going from top to bottom, are these comparators that identify the largest element for me. And that goes directly to the output. Now I have to sort 5 inputs, and this is the sorter for that. Basically, I need 4 comparators to identify the largest, and that will be the largest among those 5. 3 comparators, 2 comparators, 1. So I very quickly got to this sorting network that I'm very confident is correct. It's not the most efficient sorting network. There are much more efficient ones. But you know, the advantage of this is that the design process was simple, and I'm confident in its correctness. Okay, recursion, as those of you who do software know, that often it's sort of dismissed as being too inefficient. That's because in the course of executing a recursive program, there are many procedure calls, and each procedure call has some overhead. And in particular for recursion, the overhead basically may be larger because you have to save all the work that you did in one recursive call before you go to the next recursive call. Overhead is not as bad these days because hardware is being designed now to make procedure calls efficient because they're very important. We can do what is known as tail recursion. This is a recursive call, recursive design in which the recursive call is always in the last statement of the procedure. When the recursive call is in the last statement, then you don't need to return to that procedure. So all the work and overhead associated with return after a call is eliminated, because you just go to the next level of recursion without ever returning to the previous level. Okay, we can also unroll the recursion. Once you have designed a program recursively, you can unroll it to make it more efficient. Or you can partially unroll it. So for example, if you are trying to design an n factorial program, this is a toy example. Nobody does n factorial using recursion. But n factorial is n times n minus 1 factorial. Or you can unroll it a few steps and formulate n factorial directly as a function of n minus 3 factorial. So this reduces the number of recursive calls by a factor of 4 because you have unrolled this by 4 steps. Okay, in the case of hardware, I already mentioned the design is recursive. I'll get to examples very soon. And the circuit realization is often fully unrolled, as I showed you in the case of the sorting network. And again, to repeat, recursive design provides analyzability and reliability. Okay. There is one form of recursion that I won't talk about the rest of this talk, so I just thought to mention it and just, get it out of the way, and that's called iterative refinement. So a very good example, well-known example of that is computing square root of z by starting with an approximation x0 and then repeatedly using this formula to get better and better approximations. And this particular formula is what we call quadratic convergence, meaning it converges quickly. So if the error is, let's say, 0.1 in one step, it becomes square root of 0.1, 0.01. In the next step, square root of 0.01, 0.0001 in the next step. So it converges very quickly to the correct result. So all I need to be able to use this formula is to come up with a good initial approximation. And there are many such approximations. So this is the function, the blue curve here is the function square root of z for z ranging in the range 1 to 4. And the reason I take 1 to 4 has to do with IEEE floating point standard, so I'm not going to explain that. But this is an adequate range for the computation. So the blue curve is the actual square root of z function, and the dashed lines are various linear approximations to the square root of z, starting with the constant approximation, 1.5, which has a large error of 0.5 at the two ends. And there are various, better and better approximations that take more work initially. So you invest more work initially to get a good approximation, and then you save on the number of iterations. There's a trade-off. And then, of course, you can also use a table lookup to get a fairly accurate approximation. So this is basically what you see in this next slide, the basis of implementing that recursive formulation in hardware. The blue box on the left is a table lookup, or a lookup table, I should say, where you input several bits of z to it and get a decent approximation x0. And then each of these dark yellow or orange boxes is basically one application of this formula. So initial approximation, first, second, third, fourth. So if this is accurate to 10 to the minus 1, this will be accurate to 10 to the minus 2, 10 to the minus 4, 10 to the minus 8, 10 to the minus 16, which is basically 16 digits of precision. That's good enough for most applications. Okay, so this is also a good time to mention that I don't have to really fully unroll this recursive process. I can just implement one of these boxes if I want to save on the amount of hardware, and then use it 4 times. So once X1 is computed, I feed it back through registers, use this box a second time, then a third time, a fourth. So that's sort of the poor man's implementation of this recursive process using almost 1/4 of the hardware. Or you can do an intermediate scheme, implement 2 of these boxes, and then use them twice. So compute X0, find X0, compute X1, compute X2, then feed it back and get X3 and X4. Okay, so I mentioned this is not the type of recursion that I'll talk about. So I thought to mention it for completeness. Okay, my first example is the discrete Fourier transform. So I'm going to spend maybe about 5–10 minutes on each of these examples. The discrete Fourier transform, as many of you know, is defined as by this expression. You have an input vector x with n elements, and you have an output that you're computing, another vector of n elements. Each element of the output is a weighted sum of all the elements of the inputs, okay? So these omega n to the power ij are the weights. Omega n is a constant. Again, I won't explain why that notation is used. It's just a constant. You raise it to different powers and use it as weight for the input elements x, and then this weighted sum gives you yi. So naive computation of this expression gives you an order n squared algorithm, meaning that you have, for each element of y, you have n multiplications and then n additions to add all of those together. And then because there are n outputs to compute, this gives you order n squared. Now in the 1950s, the fast Fourier transform was discovered, which basically says the following. If you want to compute an 8-input Fourier transform, so these are the x values, inputs. These are the outputs. You take the even index inputs, x0, x2, x4, x6, and compute the Fourier transform for those 4 inputs. And then take the odd index inputs, x1, x3, x5, x7, compute those, and then basically combine u0 and v0 to find y0, and to also find y4. u1 and v1 gives you y1 and also y5. And the combination is according to these formulas. So ui plus some weight multiplied by vi gives you yi. ui minus the same weight multiplied by vi gives you yi sub y sub I plus n over 2. So y0 and y4 are computed by these 2 equations, y1 and y5, okay? Sorry for those of you who already know all of these. I want to make sure that everybody understands the next couple of slides. Okay, so in the case of recursive algorithms, we use recurrences to evaluate the time and cost complexity. So the time complexity of this algorithm basically is given by this. If you're doing sequential computation, basically you're using one processor to do this computation, you have to evaluate 2 half-size FFTs. So 2 times the time needed for the half-size plus n. N are basically the n equations of this form, or n over 2 pairs of equations. Each equation involves a constant amount of work, 1 multiplication and 1 add or subtract. Okay, so n is the order of complexity for combining these 2 half FFTs. And therefore, this gives you order n log n. So that's the sequential algorithm, which is much better than order n squared for the naive scheme. And if you do this in parallel, as you do when you implement hardware, basically the two half Fourier transforms are evaluated concurrently by different circuits. So the time complexity is the time of the half size FFT plus 1. You just need 1 or a constant amount of time to do this combination. Okay, that gives you order log n time for the parallel implementation. The inverse DFT is almost identical to that. So just the power becomes negative here. And you have this factor 1 over n. So the same circuit essentially can be used by the change in these constants to evaluate the inverse FFT. Okay, one point before I move on to the next slide, and that is, you see here, I said even indexed inputs give you the U values, odd indexed inputs give you the V values, and then you combine those to find the outputs. Now, the reason you see these even index input written in this weird form is that when you try to do the 4-point DFT among these 4 inputs, you again repeat the same process. Now, among those 4, the even index inputs are x0 and x4, basically the first, the 0th and the second, and the odd index inputs are x2, the first, and x6, which is the third. Okay, so that's why that particular order appears there. This is a 16 input FFT network shown with full detail, including that if inputs come in order x0, x1, x2, xn, then you have to do this permutation here to align them with the appropriate cells in the computation. So that you see a complete FFT network. Okay, now one problem with this, this is known as the butterfly network. It appears in all sorts of places. It's a very versatile network. It's not as good for FFT. One problem with this is that the connections in various columns are different. So if you try to implement this in VLSI, you know, the wiring pattern will be different in different stages. You have to lay out the complete network. Okay, so by shifting nodes around, I can redraw it in this form, where the connectivity becomes uniform in different columns. Therefore, if I design this in VLSI, I just lay out one of these columns and just repeat the same design 3 times. Okay, juxtapose them 3 times to get the full network. I can also reduce the wiring complexity. So if you see here, X4 is connected to 2 nodes. I can connect it to just one of the nodes and then let those 2 nodes exchange values in order to reduce the wiring complexity. Okay, so this is basically a version of the butterfly network in which connections are regular in different columns. And also wiring is reduced by this trick. Whenever something goes to 2 different nodes, I just send it to 1 node and let those 2 exchange the value. Now, one good thing about this is that I can now design an FFT processor that is much less complex by just implementing one of these columns. So I implement one of those columns and put registers here. Once this column has computed its results to be sent to the next column, it's not sent to the next column, it's sent back to the same processors. And this is almost as fast as the full implementation here, because here, even though I have 3 columns of processors, only 1 column is used at any given time. So this column must do its job and send its values to the next column before this one can start its work. So other than the overhead of the storage, okay, this is nearly as fast as this full implementation. There's also a much cheaper implementation down here that I'll skip in the interest of being able to finish on time. The second example is recursive multiplication. If you have not seen this, you know, that you'll find it very interesting. If I want to multiply two numbers, let's say two 32-bit numbers, I divide the two numbers into halves, the high part and the low part for both numbers, and then do half multiplications. Low part of A multiplied by low part of X, high part of A multiplied by high part of X, this is this number, and then high times low and high times low, these are these two numbers. And the shift amounts are basically there because, you know, this high part essentially has a bunch of zeros to its right, okay? So in order to reflect the proper weight or value for that, I have to align the result at this point. And these two, each of them has a bunch of zeros, so the shift is double that amount. Okay, so basically to multiply two 32-bit numbers, I can do four 16-bit multiplications, and then I have to add these four values to complete the process. Okay, there are actually not four values, but three values, because this first value and the last value do not overlap. So I can put them side by side as shown here. So there are three things to add: this long number in the middle and the two shorter numbers here. And then the recurrence corresponding to the complexity. So D throughout the discussion stands for delay, C for cost. The delay of this n-bit multiplication is the delay of n over 2-bit multiplication, assuming I do the four of them in parallel. So there are four half multipliers. Plus order log n, which is the complexity of this addition. That gives you order log squared n. And the cost is 4 times the cost of half multipliers, because I'm using 4 half multipliers, plus order n, that's the cost of this addition process. It's linear in n. So that gives you order n squared. Now, this is not asymptotically the best multiplication scheme. We do have multiplication schemes that have order log n delay, so less than this, and pretty close to order n log n complexity. But this is, again, one of those benefits of recursion. It's very easy to multiply. If you already have, for example, 16-bit multipliers as components, let's say you're using IP, this is particularly important in FPGAs. So you're designing something on an FPGA, and the FPGA gives you 16-bit multipliers. You need a 32-bit multiplier, okay? So you use 4 of those onboard multipliers to do these half multiplications, and then you design circuits on the FPGA for this. Okay, so even though it's not the most efficient scheme for multiplication, it's widely used. Okay, I'm going to skip Karatsuba multiplication. It's interesting, but I probably won't have time. The special case of squaring. Now, squaring appears in all sorts of places in digital signal processing applications. Of course, you can square a number by using a multiplier. Just connect the number to both inputs. That's an overkill. If you design a squarer directly, you get a simpler circuit. This is why. So suppose these two numbers, in this example, I've shown two 8-bit numbers. Okay, I'm trying, both numbers are the same. I'm squaring. So AH is the same as XH. AL is the same as XL. So AL times XL is the square, is a half squarer. AH times XH is a half squarer. AH times XL, remember, these are the same. So AH times AL, AL times AH, these are basically the same numbers. So rather than do 2 multiplications, I can do 1, and just shift the result to the left by 1 bit to get double that. So now the components I'm going to use are a single multiplier, 2 squarers, and I have to add just 2 numbers rather than 3 numbers in the previous example. So it's very common to design squarers directly because they end up being simpler in terms of circuit, therefore using less power as well. Okay, the last set of examples that I'll discuss are counting networks. As I mentioned, these are things that I've been working on recently. So what is a counting network? There are actually various classes of counting networks. And these notations are basically used, I use them to denote this. First, there are always n inputs in counting networks. There are n binary inputs. And therefore, here I'm asking, how many of the inputs, of the n inputs are 1? So question mark means how many. So I want to design a network to determine how many of the n inputs are 1s. And in the literature on computer arithmetic, which is one of my areas of specialty, these are known as parallel counters. How many 1s are there among n inputs? But these are other variants. Are there exactly k 1s among the n inputs? These I call weight checkers. So for example, there are some codes that are constant weight. So for example, every code word, so let's say the code is 16 bits wide, and every code word has exactly 8 1s in it. So to check the validity of code words, I need to verify that there are exactly 8 1s among the 16 inputs. So I design an equal to 8 out of 16 circuit. So these I call weight checkers. Then there are threshold counters. I want to see whether there are at least L 1s among the n inputs. This is called inverse threshold. I want to check whether there are fewer than M 1s among the n inputs. And finally, between limit threshold, I want to see whether there are at least L and fewer than M, or at least L and less than or equal to M minus 1 1s among the inputs. So these are circuits for which I've found applications in the work that I do. So I was interested in applying this recursive design method to building such circuit. First, let's talk about parallel counters. So I want to count the number of 1s among n inputs. I count the number of 1s among n over 2 of the inputs. And using another circuit here, the number of 1s among the other n over 2. Now, if n is even, all inputs are accounted for. If n is odd, there's that leftover input that I accommodate here. So, for example, if I have 10 inputs, then I count the number of 1s among 5 of the inputs, the number of 1s among the other 5 inputs, and this input goes unused because there's no leftover. But then when I want to count the number of 1s among 5 inputs, I count among 2 of the inputs and among another 2 of the inputs, that's 4 of the inputs. The 5th input is accommodated here as a carry in into this addition process, okay? So this is a recursive 10 input parallel counter that counts the, so these boxes are basically shorthand notations for these adders. This is a 3-bit adder. These are 2-bit adders. And these are 1-bit adders, actually half adders because they have only 2 inputs. If I had 15 inputs, then dividing by 2, I get 7 and 7 with 1 left over. 7 divided by 2, I get 3 and 3 with 1 left over. And then the 3-input counter is basically a full adder. So very simple structure. Very easy to be confident that this is a correct design. And in fact, in this case, it's the most efficient design known for parallel counters, okay? So I don't even lose on efficiency by going to this recursive formulation. Okay, for the rest of the examples that I'm going to give you in the remaining 10 minutes or so, I use what is known in digital design the Shannon expansion or decomposition. Okay, what is Shannon expansion? Shannon, one of the pioneers of digital design, observed that if I want to implement an n-variable Boolean function, f of x1, x2 up to xn, okay, that function can be formulated like this as two n-1 variable functions. One of them is a function where xn is replaced by 1, and that's multiplied by xn. The other one is where xn is replaced by 0. That's multiplied by the complement of xn. So this is the Shannon decomposition. It's easy to convince ourselves that this is correct because xn can be 1 or 0. There are only two choices. If it's 1, then this is the value of the function. And xn being 1, basically 1 times this is the same. And xn bar, xn prime is 0, so this term disappears. If xn is 0, then this is the value of the function. Xn being 0 makes this term 0. And xn being 0 makes this term 1. So it's correct. It's easy to be convinced that it's correct. So this leads to this hardware implementation. I use a multiplexer controlled by xn. So if xn equal to 0, I use the output of this box, which evaluates the n-1 variable function, forwarded to the output. If xn is 1, I use the output of this box. Okay, almost trivial. So here's how this is used to design a 2 out of 3 threshold circuit. I want to see if at least 2 of the 3 inputs are equal to 1. Okay, let's say if this input, the third input is 0, then if I want to have 2 out of 3 among the inputs, the other 2 better be both 1s. I should have at least 2 1s among the remaining 2 inputs. That's basically an AND function because at least 2 1s among 2 inputs is exactly 2 1s, that's AND. And I need to have at least 1 1 among the 2 inputs if this input is already 1, and that's OR. Okay, so this leads to this circuit for a 3-input majority function. Okay, very simple example to get us started. Okay, so more generally, if I want to do one of these weight checkers, exactly k out of the n inputs are 1s, I want to check that. Then if this last input is 1, then k minus 1, exactly k minus 1 out of the remaining n minus 1 must be 1. This input is 0, exactly k out of n minus 1. This is basically the recursive step. Then each of these can in turn be designed recursively in the same way. So here's an example, bottom left of the slide. If I want to see whether there are exactly 3 1s among the 6 inputs, each of these circles is now that multiplexer. If the last input is 1, then I need 2 out of 5 in the remaining 5 inputs. The last input is 0, I need 3 out of 5. And then so on and so forth. Until I get to the end here, where I get something like 3 out of 3 should be 1. That's a 3-input AND gate. 2 out of 2 should be 1. That's a 2-input AND gate. 0 out of 3 should be 1. That's a NOR gate. And 0 out of 2 should be 1. That's a NOR gate. And exactly 1 out of 2 should be 1. That's an XOR. Okay, so I have a bunch of multiplexers. And then at the edge of the design, I have these gates that put there. Okay, so the cost of this circuit is the cost of the multiplexers, the number of multiplexers. I call that B. So C is the total cost. B plus peripheral gates. Those are basically the ANDs, ORs, and XORs at the edge of the circuit. I have a formula for that. I haven't put it there in order to keep the slides, comprehensible, less complex. I do have a formula for that. But what is the number of multiplexers? This is the recurrence I could write. The number of multiplexer for a k out of n weight checker is 1. That's basically the last multiplexer. Plus the number of multiplexer for a k out of n minus 1 weight checker. Plus the number of multiplexer for a k minus 1 out of n minus 1 weight checker. Now, if I solve this recurrence directly, it gives me exponential cost, which is basically not desirable, and it's not correct, because that recurrence ignores the sharing of circuits that you see here. Okay, so the 2 out of 4 checker here is shared rather than putting 2. If I simply use this recurrence, it assumes that there'll be 2 copies of this, and there'll be 2 copies of that. That's not accurate. So this is basically the recurrence that I use. So 1 plus those 2 components minus the amount of circuits that I share. And then this recurrence has the solution k times n minus k minus 1. Again, if you're interested in details, I'm working on a paper where all the details are given how to solve these recurrences, but take it from me that this will be the answer. So the 3 out of 6 weight checker, just plug in k equal to 3, n equal to 6. So this will be 3 times 3 minus 1, which is 8. And sure enough, there are 8 multiplexers. 1, 2, 3, 4, 5, 6, 7, 8. Okay? All right, so that's one kind. Threshold counters. Let me skip the slide in the interest of time and show you this. So here is a threshold counter, 6 out of 8. So I want to see if at least 6 out of the 8 inputs are equal to 1. Again, I use a multiplexer. If the last input is 0, 6 out of the remaining 7 should be 1. The last input is 1, 5 of the remaining 7, and just expand in the same way until I get to these edges where this is a 6 input AND gate, 5 input AND gate, 4 input AND gate, and so on. This is a majority circuit here that I already showed you how to design. And this is an OR gate. Now again, I've developed recurrences. And in this case, the formula for the number of multiplexers is n minus L times L minus 1 minus 1. So basically, these are all quadratic costs. You know, if L is fairly small, if L is equal to n over 2, roughly in the middle, this will be n over 2. And this will be roughly n over 2. And therefore, it will be order n squared. And then if I want the other version less than, so the complement of that is less than 2 over 8, I simply can use that circuit and invert its output. Okay, so that's one way to do it. But I can also design this directly, and in this example, it gives you a simpler circuit compared with what you get by just using this circuit and inverting the output. Okay, let me just give you one more example and then conclude my talk. This is between limits threshold counters. So basically, I want to see whether between 3 and 4 of the inputs, of the 7 inputs are ones. Okay, so at least 3, no more than 4. The same principle applies. So I want, I want the number of inputs that are ones to be between 3 and 4. If one input is 1 here already, then the remaining input should be between 2 and 3 ones. Okay, 1 less than those. If this input is 0, the input that controls the multiplexer, then between 3 and 4 of the remaining 6 inputs. So it's the same principle. You just expand it, and eventually you get to AND gates, NAND gates, NOR gates at the edge. Now, interestingly, for this one, I have not been able to formulate the recurrence yet. Of course, I can design such a circuit by using 2 threshold circuits, 1 greater than or equal to 2, 1 less than 7 to do the 2-6 circuit. So if the number of ones is at least 2 and it's less than 7, then that's what I want here, okay? However, when I expand this, the structure is rather irregular, which has stopped me so far from being able to formulate the complexity in terms of number of multiplexers and the number of edge elements that are needed. And I'm working on that these days. Okay, so this slide basically shows you that regularity is a very important property in VLSI. And a prime example of that is that the fastest multiplier are tree structured. And this tree is basically very irregular. And therefore, it's difficult to implement in VLSI. Theoretically, it has better speed than what we call array multipliers. An array multiplier is highly regular and very easy to lay out in VLSI. It has short wires that improve the speed of signal transmission, but theoretically is not as fast as this one. So for the highest speed applications, we do not use this. But for applications where simple VLSI layout is a goal, and with simple VLSI layout comes also pipelining capability. So I can basically, when I input a set of inputs and they go past the first row of the cells here, move on to the second row, I can start a new multiplication. So several multiplications can be going on at once. Okay. All right, so conclusions on future work. Recursive hardware design is feasible and beneficial. I hope to have convinced you of this with the examples I showed you. I covered 3 examples, FFT, multiplier, counter, but there are other examples. For example, sorting networks. You can design sorting networks in the same way. Benefits are ease of analysis and correctness proof. They may be preferred even if they are not the most efficient, especially for low volume designs. For high volume designs, you can afford to invest time and effort to fully optimize the design. But for one-of-a-kind or low volume designs, quick design is usually a more important property than being the most efficient. All of the designs that I showed you in the previous slides can be pipelined for higher throughput. That's a big advantage. So when you do, say, many counting problems with the same number of inputs, you can pipeline the same circuit to achieve high throughput. Okay, so I'm also now working to actually physically implement these networks to determine the latency, cost, power consumption in reality rather than through mathematical models. Okay, thank you for your attention, and I'm ready to answer any questions that you may have.
Thank you very much, Doctor. Before I ask my own question, I open it to other participants. If anybody has a question, please.
Okay, let me stop my screen sharing so that I can see everybody. All right.
Payman, looks like you unmuted yourself. Do you have a question?
Just a quick one. So very interesting talk. I'm not a hardware person, but the math is very elegant and the logic is very elegant. So very nice one. Do you have an idea when it hits implementation, rough idea of the benefits, as you mentioned, on the power consumption, latency, performance, or that's TBD, to be seen?
Yeah, so basically, on one of my slides that I went through quickly, didn't fail to mention, is that when you do complexity analysis in algorithms courses, so you do the O notation. So O square root of n is much, much worse than O log n, okay? Because if n is 1,000,000, square root of n is 1,000, whereas log n, log base 2 of n is 20. However, the types of applications that I'm dealing with, the number of inputs is reasonably small. For example, 64 bits, 128 bits. So if you take 64 bits, then log of 64 in base 2 is only 6. Square root of 64 is 8. So there isn't a lot of difference between log and square root. So these circuits are theoretically inferior to the best known circuits theoretically, but in practice, they basically offer competitive. So their result is so close that you really can't make a final judgment before you implement the circuit. Because in VLSI, all the wiring patterns and stuff like that affect the speed as well. That's the part I have not done yet. I have not done actual circuit implementation.
Okay, thank you so much.
Anybody else having a question? What I have is not really a question, is more like a remark. It's about a company that was a startup here in Seattle, and the name was Xnor. I wonder if you have heard about them recently, maybe like 6 months ago. They have been bought by Apple for an undisclosed, or at least I don't know the amount, but
200 million.
Okay.
What company was that you mentioned?
The name of the company was Xnor. And when I was listening to your work, it reminded me a little bit of their line of work. Maybe, Peyman, you know better than me. Would you be able to give like a 1-minute description of what they've done?
I mean, it's hard for me, but this is a startup out of the computer science department here. Ali Farhadi was behind it, and the best way that I understand it is that they managed to do machine learning AI on mobile platforms on a live basis. So you would pick up your smartphone and you would scan an area, and as the scenery passes by the smartphone, on the spot, immediately it would say, here's a human, here's a car, here's a light pole, this is a car moving, this is a book. So the classification recognition was very, very fast, and it was tailored. It was a tight tailoring between the software optimization and the existing hardware on the smartphone. I think this was very new a few years ago, maybe 4 or 5 years ago when they started this. I think now this is maybe kind of the norm on mobile platforms, but as was mentioned, Apple bought them a few months ago, just before COVID hit, for $200 million, and it was a very, very good news for Ali.
Yeah, and somehow all the the abstraction you are making to really make this hardware more efficient, it shows how important it is when it comes to the edge computing, where the hardware costs and consumption become really, really important for companies like Apple or many other companies.
I mean, it was definitely, when I saw the demos from Xnor, again, a few years ago, it was very impressive. And I'm sure they improved it significantly over this 3-4 years. I doubt if Apple just gives that much money for something which is not state of the art. So there must be some very, very state of the art work that they were doing on the optimization side of things.
Yeah, the way I understood it is that in neural networks much of the deep learning work, there's a lot of multiplication and addition, and usually you do this multiplication and addition as large numbers like 32 bits or something. And they managed to do it in binary, meaning that each pixel would be presented as a single bit. And then getting this similar, maybe losing very little in precision.
Yeah.
That was the essence of what they have done.
Yeah.
I believe. Abdi, do you have a question?
No, actually, it was a very interesting talk. The only, I mean, 2 or 3 comments, if I understood properly. You are talking right now for the circuit design. I think you have another talk about network design using recursive network design. So my first question is, what about sequential circuit? Because combinational circuits, you know, I understand there is parallel counter and all of this. Mm-hmm. And then, reference to what Bahram said, we have lots of distributed computing, parallel computing, and for example, MapReduce, Hadoop, they are doing parallel processing. So is there any way that the design of this type of distributed processing, parallel processing, to be changed, you know, as what you said, recursive manner? Again, the reference to, I think, Bahram, what you said was added much more to Dr. Stock. For example, edge computing. To me, a recursive design, if we compare it with the software concept, should be more expensive. I don't think we can use recursive design whenever we have nodes at the edge level, because there we have less processing. As I said, I didn't have question, but there are something came to my mind. I mean, I don't know which one is related.
Yeah, I should have emphasized during my talk that this recursive approach is definitely not applicable even to all combinational circuits. So some problems are naturally suited to this formulation. So parallel counters is one example. But if you talk about, let's say, a code converter, there's no guarantee that depending on the code, there's no guarantee that, so I'm not proposing this as a universally applicable method, but when it is applicable, it's nice and leads to good results. So I should have made that clear. Now, as for sequential circuits, of course, again, those are more challenging. And also, so you have to look for each particular circuit, whether a method like this is applicable. My suspicion is that the percentage of cases where this is applicable is even less for sequential circuit than for combinational circuits.
Thank you.
Mm-hmm. Perfect. There was one of our the people on the line has a problem with the microphone, so she typed her question, and I'm going to read it. This is the question, is there a general rule for converting DFT into FFT, or is it a problem-specific design?
Okay, now, FFT is just an implementation of DFT. So any DFT can be done through the fast Fourier transform. Okay, if you look at the formula for DFT, it's basically a matrix by vector multiplication, where those coefficients or weights form a matrix. The input is a vector, and if you multiply that matrix by vector, you get the vector, the output vector. Okay, so it's a matrix by vector multiplication. So any matrix by vector multiplication scheme can be used. However, this is a special matrix. It's not a general matrix. It's not an arbitrary matrix. Numbers that you see in the matrix are related to each other. And that's what allows us to use the FFT scheme, because those are not arbitrary numbers. They're special numbers that you can take advantage of to do FFT. So DFT can always be implemented using the FFT algorithm.
Okay. So she writes again, I'm reading what she writes. I mean the slide about the graphs and making the graphs the same at each step.
Should I go back to that slide? Let me go back to that slide and see if I can answer the question. Okay, do you see the slide?
Yes.
Okay, so this is basically a very regular process. There's a rule how to rearrange. You notice that X0 in the leftmost diagram and center diagram. X0 is at the top in both cases. X1 is all the way down here in the first diagram, and it has moved up there, okay? So the rules for renumbering or reordering are fairly well known. And so this diagram is almost mechanically transformed. So this is, by the way, is known as shuffle exchange network. So a shuffle exchange network, which is this network, and butterfly network, which is this network, are isomorphic. They're the same graph with nodes just rearranged. They have exactly the same connection. So for example, you see here, X0 is connected to whatever you call that, let's say T0, same thing here. X4 is connected to T0, the same here, okay? So it's exactly the same connectivity with nodes rearranged, and there are rules for those rearrangements. So if interested, you can look up shuffle exchange network, which is constructed like this, and butterfly network, and the rules become clear how to transform this into this. Okay, it's basically a mechanical process.
Thank you very much. So maybe last call if there is any more question.
Can I ask a question?
Sure, go ahead.
First of all, I want to thank you for the talk, and it was a very fascinating, topic. And I and my postgraduate students have used this topic several times in our research project, even though we didn't have a name for that, recursion, actually. But the thing is, in one of your slides, you mentioned that we can do, time sharing instead of having multiple copies of the same modules. We can do time sharing. Mm-hmm. But I think so theoretically, it could be could improve the area, but practically, I think it limits your design because you can't do pipeline. Am I correct?
Yeah. So when you share, you can't pipeline. That's true, because you have to reuse the same blocks for various, subsequent steps, and therefore you have to keep them free until this particular computation is out before you admit another one. That's true. So it's a compromise. You can use less area, although you can't use less power, because reusing the same thing 4 times doesn't use less power than replicating it, okay? So power is actually increased. The delay is slightly increased because of latching delays, but the cost is reduced, okay? So yeah, if you want high throughput through pipelining, you have to unroll the recurrence completely. so that it's basically one pass through the circuit.
Okay, thank you.
So, anybody else? If there is no more questions, then we thank again Dr. Parhami for such a brilliant talk. If everybody can and likes, they can put their cameras on. I like to take a picture of everyone with their pictures. Yep. Thank you, Human and Mahdi, if you can do it as well, and Sima and Sepide.
You have to explain it is 11 p.m. in Toronto. So if somebody looks at our picture, there should be fair that somebody explained it is 11 p.m.
Yeah, there was a reference at the beginning when introducing me that I've been at UC Santa Barbara for a long time. That long time is 32 years for your information.
Yes,
so a common question I encounter these days, and before that I was at Sharif University for 12 years, and then in Canada for 2 years. So a common question I get these days is, when are you going to retire? And I'm sure some of you have asked that. I don't know. I'm still going strong and I'm enjoying teaching and research. So I'll see what happens.
I hope that you are doing great for a long time. So
yeah, unlike presidency, there's no term limit. So.
Okay, I took the picture I wanted, and I give everyone a last chance to say whatever they want to say before saying goodbye to everyone and closing the session. If, Sima, you were kind of silent tonight. Do you want to say something?
Yeah, no, just thank you. That was a nice talk. Thanks for organizing it, and thanks to Dr. Parhami for the talk.
Can I ask a question? Is there any, I mean, such talks from Dr. Parhami, are they kind of regular or just one-off, or because I just accidentally just came across the link and the post, and so is there any way we can get updated?
So I leave this to Dr. Parhami himself to answer.
Well, I was asked to give this talk, and I sort of enjoy giving talks. I accept it. So maybe in future, if there are other topics of interest, yeah, we can do that.
So I may add that about 4 years ago, we again asked Dr. Parhami to give us a talk, and again he accepted and gave us. But we kind of are a bit shy to ask him too often. So yeah. But if,
by the way, I'm giving a version of this, not exactly the same, a version of this for Sharif University's Computer Engineering Department. This coming Friday night, our time, it will be 11:30. It will be Saturday, 11 a.m. Tehran time. So that will be a little bit different, but probably not enough different to be worth listening to. But yeah, I do give talks quite often, and yeah, let's see how it goes, and maybe we can do it again in a couple of years.
Okay, thank you again, Dr. Parhami. Thanks everyone for staying, and people from Toronto, thanks for staying so late at night. In Iran also, in Iran is a good time, so it doesn't matter. And also in Adelaide, I believe it's not a bad time. It's very good. Okay, thanks again, and wish you all a very good, pleasant day, night, or whatever it is in your place. Okay, good.
Thank you. Bye-bye.
Thank you. Thank you, Bahram, for organizing. Thank you.
Bye-bye.
Very, very good. Thank you.